Hi everyone. Today I want to talk about unboxed types in Haskell. Let's explore. I'll explain sort of what that means in a sec. But this is all about squeezing out a little bit more performance out of your Haskell programs. And actually, I'm hoping that this video and maybe the next several videos will sort of form another little series of different things around unboxing and optimizations, and we'll eventually get to levity polymorphism. But today's really just going to be about unboxed types. So what do I mean by unboxed types? Well, Haskell tries to pretend to be this declarative language. Well, I think it succeeds at being a declarative language. But when we write a Haskell program, we like to just think of that, an expression equals its reduct, right? If I say fib 100 and fib computes a Fibonacci number, I just like to think, oh, that's just the same thing as the 100th Fibonacci number, whatever that may be. That's going to be some big number. But actually, of course, Haskell programs have to run on real hardware. And so that means that how we write our programs actually, of course, affect how fast they will run. And so we're going to be looking at lower level details to think about what do I mean even by what an unboxed type is. So a good starting place to think about this is to think about sort of ordinary data types in Haskell, right? If I write, so I have some code here. Let me write another small example though. If I write, let's look at maybe, I'll call it my maybe, just so I can write it out here without getting errors. So my maybe A, my just, my nothing. Okay, this will compile. Yes, it will. Well, what does this really mean at runtime? So it means that we have these two constructors, my just and my nothing. My nothing, well, that's just going to be some particular memory address, right? So if I have some value of type my maybe A, well, that's going to be a pointer. And so if the value is my nothing, then that's one particular memory address that holds the one my nothing constructor, the only one that exists. And so I can test to see whether a particular my maybe value is my nothing just by seeing, does it have that address? My just, on the other hand, is a little bit different because this carries a payload. So this carries some information of type A, whatever A might be. And so what this is going to be, every time we use my just, that's actually going to allocate another little memory cell, and the my maybe value is going to be a pointer to that memory cell. That memory cell will itself contain yet another pointer to hold the payload A. The reason this all has to be done by pointers is that, of course, A can be any type. It might be int, it might be double, it might be some big tree type. No matter what it is, we need to be able to know exactly what the shape is of the myJust memory cell at compile time. And to do that, that means we need a uniform representation among all of these types. So it means that in Haskell, int and double and float and all of the different user-defined types, they all need to have the same size representation. And that's going to be as a pointer. Even bool, it looks like bool should just be 1 bit long. No, bool has to be a pointer. And in bool's case, it's either a pointer to the value true or a pointer to the value false, but it's still a pointer. And so all of these pointers, well, they take up quite a bit of space in the end. And so that's what that's sort of where unboxed types come in. So before we actually get to unboxed types, let's look at this concrete example that we have and thinking about the fact that values are represented by pointers in Haskell, we can see where we might get into trouble. So first, I define a parity type that's either even or odd. I could use bool, of course, but it's much cleaner code to make a new data type, even if that new data type looks just like bool. Now, instead of writing true and false, and I have to remember, does true mean even or does false mean even? I know it because I can write the constructor out. So we create this parity type, and actually, we can make a useful num instance for parity by defining all of the num operations, right? So here we have, this is the way that different numbers add together, right? Two evens form an even plus an odd is an odd, two odds form an even. Subtraction is oddly the same as addition for parity, so we can just define that quite easily. Multiplication, we can use these rules. Odd times odd is odd. Any other thing is going to end up to be even. These operations don't make quite as much sense, and at this point we should start to think maybe the num class has a slightly misdesigned, but we're not going to really tackle that today. From integer, we can compute from integer from any number and either get, if it's even, then we get the value even, otherwise we get odd. And that's our num instance. we're going to use that to build parity integer, which is just a combination of a parity and an integer. So the idea here is that a parity integer is an integer with its parity. Now, because parity is very quick to compute, this doesn't really make a whole lot of sense. But let's pretend that computing parity is expensive. For a while, when I was trying to imagine this video, I thought I might use primality, right? Primality is much harder to determine, but it's also not quite as compositional, so it didn't quite work out so well. So let's just pretend computing parity is long and difficult here. Then a parity integer, I'm not going to define a num instance. We'll come back to why in a little bit. But here, I'm going to be able to convert from an integer to a PI, a parity integer, sort of using the obvious way. I guess I could have just used from integer over here instead of using even n again, but I didn't. I can add two parity integers, and here I'm going to add the two parities and add the two integers. And then I want to compute a big parity integer, big PI. So what this is going to do is this is essentially the sum of the parity integers ranging from 1 to 100,000. And so I do this in a slightly odd way. Again, I'm going to return back to this in a little bit, why I did it in this slightly strange way, but this is a valid way of doing it. So here I'm going to create this list from 1 to 100,000, and then I'm going to use Go to accumulate the sum of all of these together. And then at each element in my list, I'm going to convert that into a PI and then add that to my accumulator. In the end, I need to be able to extract out the integer from an integer, from a parity integer, and then my program, here I actually have a main. I don't know if I've ever had a video with a main before. And then my main is going to print out this big parity integer. So I can, oh, here I'm in GHC. I don't want to be in GHC. I want to be in the shell. So now I can compile this. And because it's a main module, I'm going to link it, and then I can run it, and it computes the sum of all of the integers from 1 to 100,000. What I really care, though, is not about that result. I care about how much we had to work to produce that result. So in any Haskell executable, you can pass in a special flag plus RTS, uses plus, not the usual minus because it's slightly strange. And then we can pass flags into GHC's runtime system. RTS stands for runtime system. So these flags are documented in the manual. The one I care about today is -s. And so if I run this program with plus RTS -s, well, it runs, so we still print out the result, but then I get all kinds of statistics on how it ran. The one I care about here is this. So we're going to ignore all of the other statistics for today. So this says how many bytes we had to allocate as we were running our program. So just to compute this, we needed to allocate 35 million bytes in the heap. So let's think about where some of these bytes are coming from. Right? Some of them are going to come from muckpi. So going back to this myMaybe example right at the very beginning, here, this parity integer type, well, it has one constructor muckpi, which then has two arguments. So at runtime, this is going to be a value of type parity integer is going to be a pointer to some memory cell. That memory cell is going to contain a one word that says that this really is the muckpi constructor, even though it really can't be anything else. And then two more words, one that points to the parity and another that points to the integer. So that means that every time I create a parity integer, I'm allocating on my machine with 8-bit words, I'm allocating 24 bits of memory for each parity integer. Now, how many of these am I allocating in my program? Well, each number from 1 to 100,000 gets turned into one of these parity integers. So that's 100,000 allocations of parity integers. So that's going to already be, so that's 100,000. So that's 2.4 million bytes. Sorry, did I get that right? It would be 2.4 million bits, I suppose, not bytes. So we're going to just multiply by 3 to get bytes. So 100,000 of these, that's going to be 300,000 bytes. And then every time we run around this loop, we're going to call add, and that's going to create yet another one of these parity integers. And so that's going to happen another 100,000 times at a cost of at least 3 bytes per. So that's going to end up to be a total of 600,000 bytes just of parity integers. And that's an awful lot when we're just sort of doing these pairs. Can we do better? So the idea here is instead of allocating fresh bytes, I really don't care about this indirection. I just want to have a pair of a parity and an integer. That's what's called an unboxed tuple gives us. So an unboxed tuple is a way of storing two pieces of information without pointers. So actually the information itself, those are stored using pointers. A parity is always represented using a pointer. An integer is always represented using a pointer. But we don't need another pointer to another memory cell to store those two pointers. So an unboxed tuple allows us to store this sort of directly on the stack without allocating memory. So let's see how we might do that. So I'm going to take all of the stuff that's unique to parity integer, and I'm going to copy it and then paste it. And now I'm going to change this all to work with unboxed tuples instead of this boxed data type parity integer. So the first thing I do is I'm going to say it's going to end up to be a new type instead of a data type. Data type always defines something represented by pointers. New type might be represented by a pointer, it might not. The idea of a new type is on the right-hand side, we're going to have the constructor here, and then, let's see, let me finish writing this out. Okay, so now a new type can only have one piece of data that's stored by its constructor. Here, the piece of data is a composite piece of data, but it's still just sort of one thing. There's only one argument to McPI. Here, this is an unboxed tuple, so it looks like a tuple, except I put these hash marks in to say I don't actually want to allocate these as pointers. Instead, this new type is really going to be just two registers on my machine that GHC will keep track of and sort of move things around together. But no pointer, no sort of data structure wrapping these together. Now, of course, I'm defining all of these. This parity integer here is like my old one, but different. And so it needs a new name. So I'm going to follow a GHC convention and put a hash mark at the end of all of the names I'm going to define down here. So we're already going to run into trouble. So let's comment this stuff out because that's going to cause more trouble. And let's try to compile and see what we get. Operator applied to too few arguments. Yeah, so that's kind of silly. How did I just put a hash mark at the end of a name? Well, that is the magic hash extension. Notice we get a different error now. Magic hash allows us to put any number, including 0 of course, of hash marks at the end of a name, and it still forms a valid name. And that's to allow this naming convention of writing unboxed things with hashes at the end. It is just a naming convention. There's no reason we need to do this, but it's a useful naming convention so that readers know, there's something slightly tricky going on here. Now we get another error. We have operator applied to too few arguments. Well, what's happening here is that this syntax, this paren hash syntax, is special, and we need to enable that separately. So that's unboxed tuples is the extension. And then now if I try to load, now a new type cannot have an unlifted argument type. Perhaps you intended to use unlifted new types. So let's do that, in fact. And now all is well. So I've been using the word unboxed. The error said something about unlifted. What's going on there? An unboxed type is one represented without using a pointer, as I've been saying. An unlifted type is one that doesn't represent bottom. There are a few types in GHC which are boxed but unlifted. Array hash is one of these things. But normally these two terms travel together. And so the particular restriction around new types is really around unlifted things, not just unboxed things. So that's why we have to call it unlifted new types. But really, we should just be thinking about whether or not there's a box. That's the more interesting distinction for us. Okay, so we have our new type. Now we can start defining functions. So this is pretty easy. We just add some hash marks. And if we do this, well, that's close to it, except here I still have to use another the unboxed tuple constructor here. Right? This works just like box tuples, but with hash marks. So I think that should be okay. It is. Add is going to be similar. We're just going to change the name and change the type to use a bunch of hashes. And then now here we have more hashes and commas. And more hashes and commas. And then even more over here. but I don't need the inner parentheses. Okay, does that work? Oh no, what did I do wrong? I did something wrong. Oh, mcpi, it needs to be mcpi hash, doesn't it? You probably saw that. Okay, there we go. Now we can do big PI. And we put hash marks, and more hash marks, and more hash marks, and more hash marks, and more. And do we need any more? Oh, we need add hash and PI from integer hash. Maybe that's enough? No, of course not. What did I miss now? Oh, top level bindings for unlifted types aren't allowed. So here I'm saying that big PI hash is a parity integer hash. And I said briefly before that something that's of unlifted type, and all unboxed types are unlifted, right? Because if we don't have a pointer, we have no way of representing the thunk of an unevaluated thing. Right? Because let me just expand that out a moment. If we have something that's unevaluated that would be lazy, that has to be represented by something at runtime. And so the way it's represented is by a thing called a thunk, which is a pointer to a small structure that contains some auxiliary information, as well as a code pointer, sort of where the machine should start executing next. If we don't have a boxed representation, then there's no way that we can be lazy. And so big PI hash here has to be strict. But if it's a top-level binding, when do we evaluate it? Is it when the program starts? Is it when we first mention big PI hash? We really don't know. And so GHC doesn't allow a top-level binding for an unlifted thing. So we just do this. We make it a function that goes from unit to this parity integer hash. And then I'm just going to ignore the argument. That makes the problem go away. Okay, so lastly, we have to convert this. And here we just add a whole lot of hash marks and some parentheses and then more hash marks. Okay, oops, there. Need the space there, otherwise it looks like the magic hash again. That works. And then now my main, instead of using big PI, I want to use big PI hash. Of course, now I have to apply that to unit. And then this integer from PI is going to be integer from PI hash, which, by the way, just returns a regular old integer. So does this compile? It does. Let's go back to the shell. Now let's remember, it used to take 35 million bytes. Now, if I compile Unboxed and then run it, let's see what happened. We're down to 26 million bytes. We lost nearly 10 million bytes of allocation by using unboxed tuples instead of the boxed data type that we had before. So our new code is uglier, but actually it works better. And so this is because we knew that we didn't want to be allocating tons and tons of mcpi nodes. When we have a new type, this mcpi hash, that's just to sort of help organize our code and help keep our types straight, but it doesn't actually do anything at runtime. That's the beauty of new types, is that a parity integer hash at runtime is really just this thing, which is really just a parity and an integer with no extra stuff. This is really nice. I could probably work out exactly why we lost this many bytes. We're not going to right now. That's actually even more than I expected to lose. And we might think, does this mean that every time we write performance Haskell code, we have to do all of this? The answer, gratefully, is no. So let me go back to the program. I'm going to change it back to use the old big PI. So now there's this redundant brackets, but that's okay. We'll save that. And then now let me compile and run. And we see that now we should be back to this 35 million bytes. They're almost 36. But if I turn the optimizer on, and let me force recompilation. If I turn the optimizer on, let's do that. Now I'm going to take, this is the program using the original easy lifted one, but now it's been optimized. And let's see how this runs. Ooh, look at that. That's really good. Let's just see, just for comparison, let's see how that fares on the unboxed version. So now I'm going to compile this optimized and run it. Whoops. And down here we see actually the unboxed one allocates more than the boxed one. And that's because the optimizer is expecting you to use lots of boxed types. So I think in a future video, we might come back and look at exactly what's going on under the hood here. So the upshot of this last little thing around enabling the optimizer is, do we have to go to all of this unboxed stuff to get fast code? No, we don't, because we have an optimizer working for us. But sometimes we will want to do this just to be sure that we're not allocating. One last angling piece here is, why didn't I just define a num instance? Why did I write this big PI in such a strange way? Why didn't I just, fold sum? There's much better ways of writing this. The problem is that because unboxed types are not represented by pointers, there's a lot of things that we can't do. So, for example, what I might try to do here, let's comment out this go. Instead, maybe I just want to say folder sum, what would be PI from integer hash 0, 1 to 100,000, right? So if you're not as familiar with folder, let's not worry about that right here, but this should work the same way as the original code. But if I try to write this, I get an error, couldn't match a lifted type with an unlifted type. And that's because folder here is a function. It's in the standard library. It's already been written. And that function needs to have compiled code that moves pointers around. What else is it going to do? It's expecting everything to be a pointer. But suddenly my parity integer hash, it's not a pointer. It doesn't fit the schema that folder is expecting. And so we get an error, couldn't match a lifted type with an unlifted type. So working with these unboxed or unlifted types is a challenge because we have to sort of avoid using a lot of the combinators that we take for granted. I could write another version of folder, maybe called folder hash, that does work with unlifted types. That would be fairly easy to do, but it's not built in. So these unboxed types often do provide some amount of obstacle. Turns out that some of that is easy to overcome, as we'll explore in a future video. I hope this has been interesting. Thanks very much for watching. Bye.